No questions. Everything was clear, right? Very well. So today we are going to solve some task on normally distributed random vector, and also maybe we discuss some properties of characteristic functions. We'll see. So this is the assignment for this week. Let's start with number 1. So in number 1, we have a random vector which consists of 3 components. If we deal with a random vector, it means all of these components also random variables which are normally distributed. So if we have a normal vector, then each component also a normal variable. And these two parameters, the column mu and the matrix k, they are characteristics of this random vector, normally distributed random vector. And
Sorry, did you already collect attendance?
not yet.
Okay.
So in case of n-dimensional random vector, mu will be expected values of its components, and k will be a covariance matrix. And so on. So everybody knows how covariance matrix looks like. Okay, in our task, we have 3-dimensional random vector, and we need to find the probability density functions for each component and for a random vector which consists of 2 components, first and third of the initial random vector. So how to find the PDF for the first component? Let me introduce you to approaches. They are very similar. The first one, which is slightly more difficult, more complex, I'm sorry, is the following. So if we have some random variable t, which is a linear combination of other random variables, which are normally distributed, there's this random variable t has also normal distribution with some parameters, with parameters a prime and sigma square. Because I used a here, I just try to put here another value. Okay, how to find these parameters? Again, according to the theory, it will be the following thing. Let me denote with t, meaning the transpose, the column vectors. Okay, and sigma square will be, so this will be vector v, vector v multiplied by matrix k multiplied by vector v transposed. If we use this idea, then we can say that for the first component, it's actually 1 multiplied by xc plus 0 multiplied by eta plus 0 multiplied by zeta. So in our case, vector v is equal to 1, 0, 0. And we can say that expected value of x is equal to 1, 0, 0 multiplied by 1, 0 minus 2, which it is equal to 1. And sigma square is equal to 1, 0, 0 multiplied by matrix K multiplied by the column 1, 0, 0. So if we do this multiplication, we get 2 in the end. So this random variable xc is normally distributed with parameters 1 and 2. The question is find probability density function. So what will be the probability density function in this case? It's equal to, for random variable, it's 1 divided by square root of 2 pi multiplied by sigma e in the power of minus x minus mu square divided by 2 sigma square. In our case, it will be 1 divided by 2 square root of pi e in the power of, so it will be x minus 1 in numerator and 4 in denominator. So this will be the answer for the very first question. So once again, if you have some linear combination of random variables, then this new random variable is also a normally distributed random variable. And you can easily find its parameters, its expected value, and its variance using the initial knowledge of the random vector. Another way to solve such task, for instance, what is the f2 of y?
Sorry, vector v is any vector we want. For example, we can choose 0, 1, 0. Yes?
Yes. For instance, if you take a look on 1b, then here we see that vector v is 2, minus 3, and minus 1. So this vector we get after we make a linear combination. And for the f2 here in 1a, we need to make such linear combination that we have only y. So in this case, it will be 0, 1, 0, right? It will be 0 multiplied by xc plus 1 multiplied by eta plus 0 multiplied by zeta. Okay, but now I want to speak about another way to solve this. What happens? Of this task. So as I said before, these parameters, we know what are the numbers here. And we can see easily that so this mu is actually expected values of the components. And we can take the expected value of y directly from here. So first of all, again, we say that it is normally distributed random variable because it's a component of the random vector, which is normally distributed. So its component also normally distributed. And its parameters will be 0 in our case, and sigma square. Sigma square we take from the matrix K. Where is it? It's here in the very center. So here 6 is equal to variance of eta, right? It's covariance eta eta, which is variance. So as you see, slightly faster, we understood what is the random variable we deal with. So in this case, the PDF will be 1 divided by, so it will be square root of 6 multiplied by square root of 2. It will be 2 square root of 3 pi multiplied by e in the power of, so here we have x squared, not x, but y. And here we have 6 by 2, it's 12. So this will be the probability density function for the second component. Okay, the same idea for the third component. You can do it at home, nothing difficult here. The more interesting case is the last one. So what is the probability density function for the random vector x and z? So this random vector has only 2 components.
Sorry, can you explain, please, how did you find the variance of y?
Yeah, sure. Actually, here in the covariance matrix on the diagonal, you have a variances, because this covariance x1, x1 is actually equal to variance x1. And this is the last covariance, is variance xn. So here in the task, if we take a look on the condition, we have this matrix. And here 2 is a variance of xc. 6 is a variance of eta. And 1 is a variance of zeta. So we take it directly from the matrix. And here we have the expected values. So this is expected value of eta.
Thank you.
Yeah, you're welcome. So I ask you to solve this part. Find the f13 of x and z. Just a quick reminder, how does this probability density function look like in case of random vector? You had it on the lecture, but let me remind you. So here, so you have some coefficients before the exponent here and the exponent itself. Here you see the covariance matrix in the power of -1. And here on the left and on the right are 2 vectors. And it's the same vector, but one of them is transposed. So this is how the PDF looks like. Okay, so it should be enough for you to solve this task. Send me the solutions. Any questions, please ask.
Sorry, can I ask you a question?
Yes, sure.
So when calculating the determinant of the sigma, which is in our case k, should we calculate the determinant of the whole matrix, or we take into account only 1 and 3? I mean xi and the last letter.
Zeta.
Yes.
Mm.
Should we calculate the determinant of the whole matrix?
So why do you need to calculate the determinant?
To calculate the marginal probability density, F13.
All right. Then for this matrix, you have only 2 dimensions, right? So it should be determinant of 2-dimensional matrix. Not, yeah.
Oh, okay.
Mhm. Okay, guys, any results? So as I said before, here we have to find the PDF of a random vector, which consists of two components. And in this case, vector mu will be equal to, let me write it like this, the expected value of xi and expected value of zeta. And if we take a look on the condition, we see that expected value of xi is equal to 1, expected value of zeta is equal to -2. So it will be 1 minus 2. Okay. The covariance matrix also have two dimensions. It has two dimensions, and so we have to find the four numbers. Number on the place 1, 1, it will be variance of xi, and the variance of xi we see here. It's 2. Well, let me write it in more details. So okay, this is variance variance xi. Here we have covariance xi eta. Here we have covariance xi eta. Not eta, but zeta. Anyway, I write it the same way. And variance zeta. Okay, but we already know these values actually. So here we have 2. This will be the variance of xi or xi. -1 will be the covariance of xi and zeta. -1. And the variance of zeta is 1. It's written here in the position 3, 3 for the third component. Okay, this is the matrix K. What is the PDF in our case? So we have a two-dimensional vector. It means that K here is equal to 2. So we have 1 divided by 2 pi. Then we have to put here determinant of the matrix K in the power of -1/2. Okay, what is the determinant of K? Did someone already find it?
3.
3, really? I have 1. So 2
Yes.
multiplied by 1 minus -1 multiplied by -1, it will be 1. Okay, yeah, 1. Okay, so we don't have to write anything else here in the denominator. Then we have to multiply this by exponent. So -1/2 here. Then we have to put this vector x minus mu. In our case, it will be x minus 1, first coordinate, and z plus 2, the second coordinate, right? Because our vector is x, z. So it will be the vector x in the definition on Wikipedia. So the vector x minus mu will be the vector x minus 1, z plus 2, right? Just in case somebody didn't understand how I put here. Okay, so we have matrix K, but here K in the power of -1. So we have to find the inverse matrix. Is there anyone who already found the inverse matrix?
First row 1, 1, second row 1, 2. If I calculate it correctly, don't know.
So this is the same student who calculated the determinant, right? Okay, I hope now you didn't make a mistake. Okay. So this is the answer, but we can simplify it, of course. Well, let's do it. Why not? So let's open the brackets. So it will be x minus 1 in the power of 2, then 2 times x minus 1 by z plus 2, plus 2 multiplied by z plus 2 in the power of 2. So this expression I like more. So this will be the answer. Okay, is it clear? Any questions?
Clear.
Lovely. Let's move on. And now we maybe solve 1b. So in 1b, we have to find the probability that this random variable is less than 9. As I said before, somewhere here, if we have a linear combination of normally distributed random variables, then we have the random variable which is normally distributed as well. So this random variable, let's write it with letter t, to psi minus 3 eta minus zeta. It is normally distributed with some parameters a and sigma square. Let's find out what are these parameters. So we have this vector v, which is 2 minus 3 minus 1, and a equals to v multiplied by mu transpose. So it will be 2 minus 3 minus 1 multiplied by mu, and mu is 1, 0, minus 2. We do math here. 2 plus 0 plus 2, it's 4. Okay, sigma square is equal to v multiplied by k multiplied by v transpose. So we have 2 minus 3 minus 1, 2, 3 minus 1. Oh, it should be 3 here as well, sorry. And the column is 2 minus 3 minus 1. Okay, so first we multiply the row by the matrix, by each column of the matrix. So it will be 4 minus 9 minus 5 plus 1 minus 4. Then for the second column, it will be 6 minus 18 minus 12 plus 1 minus 11. And finally, minus 2 plus 3, it's 1, minus 1, 0. We multiply it by the column 2 minus 3 minus 1. So then we have minus 8 plus 33 plus 0, which is 25. All right, so this random variable is normally distributed random variables with variable with parameters 4 and 25. I like the number 25. We can easily take a square root of it. Okay, so we need to find the probability that t is less than 9. Let's normalize t in order to use a table for random variables with parameters 0 and 1. So we have to put minus 4 in order to get 0 in this place, and divide everything by square root of 25 in order to get the variance equal to 1. So 9 minus 4 divided by 5. So this random variable here, it is normally distributed with parameters 0 and 1. So we can use a table for normal distribution for this random variable. So it will be the value in this table for the argument 1. What kind of table is that? Here. So it's 0.84134. So this will be the answer for B, part of the B. Questions? No questions. Okay, I ask you to solve the second part of this question. Find the probability that absolute value of 2 eta minus 5 zeta is less than 16. And send me your solutions. Any problems with the solution? Do you need more time?
Yes.
All right, several people already solved this task. Let's take a look. Rizwan, describe your solution to everyone, please.
Should I present the solution?
Yeah.
So, okay. First of all, I calculated the mu and sigma squared parameters for the distribution T. That is, and then I got that T distributed with parameters 10 and 69, and it is by formula, it is root of 69 multiplied by the standard normal distribution plus 10. Then by this, I expressed the standard normal distribution through the new distribution that we calculated. After that, I expanded the sign of the absolute value, and I substituted the concrete values of the Laplace function. And then I, using the fact that capital phi is equal to the capital phi 0 plus 1/2, I got the following formula. We see that 1/2 and 1/2 canceled out, and we have that we have to calculate the phi 0 of the 6 divided by the root of 69 plus phi 0 of 26 divided by the root of 69. I just confused about the whether I'm correct with my calculations, but I think that the idea of solution is correct, at least.
Mm-hmm. Okay, any questions regarding this task?
Can you once again explain how to deal with phi function? I got that we need to, I got phi of 6 over root of 69 and phi over 26 over root, and how to deal with this.
Okay, when we covered the topic of the normal distribution, we had the formula on lecture that the capital phi is equal, I mean, the capital phi 0 is equal to the capital phi minus 1/2. This is because in capital phi, we cover the interval from minus infinity. But in the phi 0, we just throw out the negative part, and thus we have to subtract minus 1/2. And from this, we get that capital phi is equal to the capital phi 0 plus 1/2. This is just the formula. Did I answer your question?
Okay.
Okay, lovely. So task number 2, you can solve yourself. The same trick here. So these random variables u and v, they are normally distributed random variables. And to find the characteristic function of these random variables, you just can use the hint or just definition of the random of the characteristic function. And the characteristic function will be the exponent of the following, well, the following expression, nothing difficult. A couple words about characteristic functions. This is just another way to define the distribution. Usually it's more simpler way, I mean, by writing out the characteristic function. That's it, I guess. And it has some nice properties. Sergey also mentioned this on the lecture. All right, so let's move on to task number 3. In task number 3, we have a probability density function of some random vector xi. And we need to find the constant a, the vector of mathematical expectations mu, and the covariance matrix k of this vector. So as you see from the PDF, it very looks like the PDF for a normal distributed random vector. And it is actually such distribution. So you just have to find out mu, k, well, and then you can calculate a. I guess it's not difficult. Okay, so solve it, please, and send me your solution or ask me questions.
Only A or B also?
Well, let's do only A, because B, like, okay, we already calculated the probabilities today for normal distributions. No need to waste more time on it. You know how to do that. Only A.
So to find the
Yes.
Sorry, to find the A, we should integrate all the real line.
Yeah, this is the one way, but I advise you to use another method. So you know already how does the PDF look like for normally distributed random vector, and you can find out this coefficient easily. Where is it? So basically this coefficient is here, what is before the exponent. right? But also, if you like integrate and you do it fast, you can do it. I don't mind.
Sorry, could you?
The solution.
So how is it going? Okay. So from the expression of the PDF, we can see that the vector mu we can get from this expression. So you see it's x1 plus 3 everywhere. And if we take a look on the PDF for the vector, we see that it is x minus mu multiplied by a matrix, well, let me say k in the power of minus 1, and x minus mu transposed. So we can conclude that mu has the coordinates minus 3. Then for y, it's for second component, it's 2. And for the third component, it's minus 1. So I hope everybody get this result. All right. More interesting is what is the matrix k in the power of minus 1. By the way, here should be minus 1/2 in front of the expression. So did anyone already get the what is the matrix k minus 1?
I can try and you can check if it's correct.
Okay, tell me, yeah, tell me the numbers.
Minus 1/2, 1/2 and 1 is the first row. Second row, 1/2 minus 1 minus 3 over 2, and 1 minus 3 over 2 and minus 3.
So that's right. If we take a look on this expression, we see that here we have minus 1/2. It will be the diagonal element on the first place. Here minus 1 on the second place. Here is minus 3. It will be a third diagonal element. Then we have some coefficients here before these two terms. So it's plus 1 here. We have to divide it into two parts, half here and half here, because the matrix is symmetric. And you see it if you open the brackets when you multiplicate vectors and matrix. Here we have 2, so it means that it will be plus 1 here and here. And here we have minus 3. It means that it's minus 3 over 2 here and here. Okay, cool. Then in the expression for PDF, we have minus 1/2 in front of the expression in the exponent. So we have to factor out minus 1/2 of this matrix. And then we get the matrix. It will be matrix k in the minus first power, and then it will be 1, minus 1, 2, minus 2, I mean. So here it will be minus 1, 2, 3. Here 3, minus 2, 6. So here we have matrix K in the minus first power. So what we already know? We already know mu. And now we can calculate matrix K. Did anyone finish this calculation? What is K? Nobody, right? Okay. So we have K minus first.
-2. In the first row, it should be
Oh, yes.
1,
Yeah.
-1, -2.
-1, -2. And here -2, 3, right? So now it's correct. Sorry, I made a mistake in annotations. Okay.
No, 3 -2. And I guess, oh no, sorry, my mistake.
You can search for the inverse matrix another way. This is just the way I got used to calculate it.
Maybe we can do it by ourselves, and let's proceed with other parts of the task, like random vector and
You think so?
constant. Yeah, I think we can find inverse matrix.
Okay, okay.
Because we have only 10 minutes.
Yeah, but I mean, why didn't you find it during the time I provided? I thought this is the problem, and that's why I solved. Okay. Anyway, here we have this matrix K, and then for us to find A, we need just to use this formula. So we have to find 2 pi in the power of -3 divided by 2, and the determinant of the matrix K in the power of -1/2. That's it. By the way, any questions regarding this task? Maybe you have something to ask. No questions. All right. All right. Also 3B you can solve yourself. Number 4 is the same. Nothing new here.
What is the random vector Xi there? How can you write it for this task as an example?
Number 4?
Yes. Or for number 3, it doesn't matter.
You asked me about the vector Xi.
Yes.
But it's written here. So Xi has 3 components, and
what is each component of Xi?
what do you mean? If you need to find the what is each component, it's a normally distributed random variable, and like it's like marginal distribution, right? So the expected value of Xi1 will be equal to -3, and the variance of Q1, Yeah, will be from the matrix K. You can take it from matrix K. Yeah. All right. Number 5 and number 6, let me skip it because here we speak about conditional probabilities. We didn't discuss conditional probabilities on the lecture. Let's solve number 7 for the rest of the time. So we have 100 independent and identically distributed random variables. We form 2 new random variables, eta1 and eta2. And we need to find the probability density function of the vector eta, which consists of these 2 components. Let's maybe solve it together because we have only 5 time left. So my first question to you, how do you think, are these random variables independent? So we have eta1, xc1 plus xc2 plus and so on plus xc40 and eta2 up to 100.
They are dependent.
So dependent, right? Is it clear for everyone that they are not independent?
Not exactly.
Well, first idea is that these random variables, they are also affect the random variable eta too. So it means they are dependent. But this like intuitive way to realize if it's independent or not. But you always can calculate the covariance of eta1 and eta2. And you see that it's not equal to 0. It means that they're independent. But we will calculate it anyway. So, all right, they're dependent.
Can I ask a question?
Yes.
Correct that if we have, for example, xc1 and we have also the second variable, then these variables are dependent because they contain in their expressions the same random variables.
Yeah. But if you had like xc1 plus xc2 plus and so on plus xc40 and xc41 plus xc42 and so on, then they're independent. But if you have here xc40 plus everything else, they become dependent because by defining these variables, you also somehow influence this whole expression. All right. So my second question, are they normally distributed?
Yes.
Of course they are, because this is a linear combination of normally distributed random variables. What next? All right, then this is normally distributed random vector, right? With some vector mu and some matrix K or sigma, how you like it more. Okay, what is mu? Can you tell me? So expected value of nu1 is sum of expected values of xi when I changes from 1 to 40. Each of them equal to 0, so it will be sum of zeros, it will be equal to 0. And for the eta2, it's also 0. Okay. What about matrix K? So by definition, covariance matrix is the following matrix. So can you tell me the values? For instance, what is the variance of eta1?
1.
That's strange why you tell me this answer all the time. Like previous group, the same answer. It's not 1. So variance eta1. This is the variance of Xc1 plus Xc2 plus and so on plus Xc40. So any other options?
40.
Yeah, because they are independent, we can say that the variance of sum is equal to sum of variances. Each variance separately equals to 1, so it will be 40. So it means that our matrix K has 40 here, some number here, and 100 here, right?
Can I ask a question?
Yeah.
Why is every xi independent, like 1?
It's according to the condition. IID means independent and identically distributed. Somewhere here as well. Oh no, that's weird. I saw it in the, it was another document. Okay, IID means they're independent and have the same distribution. Okay, and finally we have to find the covariance of eta1 and eta2. Did anyone know? Did anyone solve this already? Know the covariance? Can you tell me the result? So covariance is a linear function. If we use this property, then we have sum of such covariances where I changes from 1 to 40 and J changes from 1 to 100. If I is not equal to the J, then covariance is equal to what? I think 0, because they are independent, so covariance is equal to 0. But if I is equal to J, then what?
1.
Yes, because this is a variance, so we have to actually sum up 40 times number 1. So we have 40 here and 40 here. So we found everything. So we defined our distribution of random variable. We found vector mu and matrix K. And knowing that, we can easily find the probability density function, right? You know how to do that here, the formula. All right, that's it. If you don't have any questions, please write your email addresses in the chat on the Zoom. And that's it for this week.
Okay, thank you. Bye.
You're welcome. Bye-bye.
Also, sir, can I ask you a question about the lab 7?